Welcome back, everyone. We're taking a deep dive into something pretty essential today, uh, aircraft weight and balance.
Uh-huh.
We'll be using some excerpts from handbooks, so get ready for some seriously geeky aviation talk.
You might be surprised by what we learn.
Yeah,
It's not as easy as just spreading everything out evenly,
right. That's what's so fascinating about this.
Yeah.
We're going to discover why perfectly balanced planes aren't always the safest option,
Uh-huh.
and how planes can actually gain weight as they age,
Oh, yeah.
just like us.
That's right. Every little detail can make a difference when it comes to keeping things safe and efficient up in the air.
Right. Okay, so let's break this down a bit.
Uh-huh.
Why is weight and balance so crucial? We all know it matters,
Hmm.
but let's connect the dots for our listeners.
Okay, so think about riding a bike that's all wobbly and unbalanced. It's tough to control, right?
Yeah.
Now imagine that feeling, but in a plane, zooming at hundreds of miles an hour.
Oh, wow, yeah. Suddenly weight and balance feel a whole lot more important.
Exactly. And it goes beyond just preventing crashes.
Oh, I see.
Weight and balance affect everything,
Okay.
from how much fuel gets burned to how high the plane can actually fly.
So it's about getting the most out of the aircraft performance.
You got it.
Yeah.
If the weight isn't right, you could end up with less fuel efficiency,
Mhm.
reduced range.
Yeah.
It can even mess with the plane's ability to climb or make those fancy maneuvers.
Makes total sense.
Yeah.
So how do we even start figuring this stuff out?
Hmm.
I've seen terms like datum, arm, and moment thrown around in the handbook. Is this where the physics lesson starts?
Oh, no. It's simpler than it sounds.
Okay.
Think of the datum like the zero mark on a ruler or
Yeah.
starting point.
Okay, our reference point.
Exactly. Now, arm is just how far something is from that datum.
Okay.
It's like saying each passenger is sitting a certain arm distance from that starting line.
Gotcha. So it's not just about how much each person weighs, but also where they're sitting. You're getting it. Now, moment is where it gets a little trickier. But picture a seesaw. You know how a heavier kid closer to the middle can balance a lighter kid further out?
Yeah.
Moment is kind of like that balancing force. It's figured out by multiplying weight by arm.
Okay, the further out the weight is, the bigger the moment. And this all leads us to center of gravity, or CG, right?
You got it. The CG is the point where the aircraft would balance perfectly if you could somehow hang it in midair.
But you mentioned earlier that a perfectly balanced plane isn't always the safest.
Right.
That seems counterintuitive.
It is. We'll definitely get into why that is.
Okay.
But first, we got to figure out how we even know the weight of the plane itself.
Good point. Do they have like giant aircraft scales for that?
They do. Every aircraft gets weighed at the factory to figure out its empty weight. It's like getting a baseline measurement. They also find the empty weight center of gravity, or EWCG, at this time.
So that's our starting point. But what about all the stuff we add on later: passengers, luggage, fuel, all that? That's where it gets interesting. Planes, kind of like us, need their checkups.
Okay.
And sometimes those checkups include reweighing.
Reweighing.
Right.
Why would a plane need to be reweighed?
Well, things change over time. There might be some big repairs.
Yeah.
New equipment gets put in.
Right.
Maybe the plane's original empty weight isn't so accurate anymore.
Hold on. Are you saying planes actually put on weight over time?
It happens. Think about it repainting without taking off all the old paint.
Oh, yeah.
Adds weight.
Huh.
Dirt and grime can build up too.
Ah.
Even those tiny additions can add up over the years.
Wow. Never thought about that. So tell me more about this weighing process. What kind of scales do they use?
There are two main types.
Okay.
Platform scales, which are basically giant heavy-duty bathroom scales.
Okay.
And then there's load cells.
Mm-hmm.
These get placed under each jack point.
So they actually lift the entire plane up to weigh it?
They do. And they have to make sure it's level, perfectly level,
Wow.
in its normal flying position to get an accurate reading.
It sounds like a super meticulous process.
It is. They even factor in things like chocks.
Those are the things that stop the wheels from rolling, right?
Exactly. And the weight of the fuel, too.
Really?
Precision is super important when it comes to weight and balance calculations.
Okay, so we've got this meticulously measured empty weight,
Mm-hmm.
and we know the plane might gain a bit over time. But how do we know how much we can safely add to that weight? There must be some limits.
You're right. That's where the CG range comes in.
The CG range.
Think of it as a safe zone for where the plane's balance point should be. We want to ensure all that loaded weight and the center of gravity stay within certain limits.
So it's not just about finding the center point, but staying within a specific range around it.
Exactly.
How do we know what that range is?
We check the aircraft's Type Certificate Data Sheet, or PCDS.
The TCDS.
You can think of it as the aircraft's rulebook.
Okay.
It lays out all the crucial info, including the specific CG range for that make and model. And It can get super detailed. You might find limits on how much fuel you can have with a full load of passengers or rules about where to put luggage based on its weight.
So it's a delicate balancing act.
Oh, it is. And there's even a visual representation of the safe zone.
Okay.
It's called the CG envelope.
Mm-hmm.
It's a graph that shows the acceptable range for the center of gravity based on how much the aircraft weighs.
So it's like a map for keeping the plane balanced.
A very important map.
I'm starting to grasp the complexity here.
Yeah.
We have our safe zone, but how does a pilot make sure they stay within it when loading up the plane? This is where it gets really exciting, right?
Right.
Okay, so we've got our CG range, this safe zone marked out on our map, but how does a pilot actually use this info
Right.
when they're loading up the plane for a flight?
Well, that's where it turns into a real-life puzzle.
Uh-huh.
The pilot has to think about everyone's weight,
Okay.
their bags, the fuel they need, and how it's all spread out inside the plane.
So they're like constantly running these weight and balance calculations,
Yeah.
taking all those variables into account.
They are. And that's why understanding these concepts is key, not just for pilots,
Yeah.
but for anyone involved in aviation.
Okay, so walk me through an example.
Uh-huh.
Let's say you're a pilot prepping for a flight with 5 passengers.
Mm-hmm.
How do you even start figuring out if you're within that CG range?
Well, they use a loading chart
Okay.
and the info from that TCDS to make sure everything fits within the safe zone,
Okay.
the one we see on the CG envelope.
It's almost like a game of Tetris trying to fit everything in the right spot.
Huh. You could say that. And if the CG ends up outside those limits,
Yeah.
the pilot might have to think outside the box. They might move passengers around,
Yeah.
rearrange bags,
Okay.
even add some ballast.
Ballast. Wait, are we talking about adding extra weight to the plane?
Sometimes you gotta do what you gotta do.
Oh, good.
It's kind of like adding weights to a car tire to balance it.
Yeah.
It's just a way to fine-tune the balance and make sure the CG stays within the limits.
So there's a method to the madness.
Yeah.
It's not just chucking sandbags in the back randomly.
No. There's a whole formula to figure out how much ballast you need
Really?
and where to put it to get that perfect CG.
That's so cool. But before we get too deep into ballast, you mentioned something earlier called adverse loaded CG checks. What are those all about?
That's where things get interesting. We're talking about pushing the boundaries,
Okay.
simulating those extreme situations where all the weight is in the front or the back of the plane.
Okay, so worst case scenarios. But do pilots really have to worry about stuff that extreme?
More often than you'd think. Think about a small cargo plane
Okay.
loaded up with heavy equipment in the back,
Yeah.
or a passenger plane where everyone decides to sit up front.
Okay.
These things might not happen every day,
Right.
but they can happen.
So it's about being prepared for those potential issues and making sure that CG stays within limits even under unusual circumstances.
Exactly. The handbook uses this great example of a stick airplane to show how different loading scenarios can affect balance.
Okay.
Imagine a stick figure like the simplest drawing that represents the aircraft. If we pile a bunch of weight on the nose, the stick's going to tip forward.
Yeah.
To
Yeah.
balance it out, we got to add weight to the tail.
Makes sense.
That's basically what we're doing with these adverse loaded checks.
So finding the limits of that safe zone, figuring out where the tipping point is.
Exactly. By doing these checks, we can
Yeah.
ensure that no matter how the plane's loaded, that CG will always stay within the acceptable range.
It's amazing how much thought goes into keeping things safe in the air.
Yeah,
It really does feel like every little thing counts.
it absolutely does.
Yeah.
And as we mentioned earlier, sometimes those little things mean adding a bit of extra weight in just the right spot.
Let's circle back to ballast.
Okay, ballast.
Yeah.
We touched on it before, but tell me more about the different types.
And when a pilot might choose one over the other.
Okay, so there are two main types, temporary
Mhm.
and permanent. Temporary ballast is usually bags of sand or lead shot,
Okay.
and it's used for certain flight conditions and then taken out afterwards.
Okay.
It's like packing an extra suitcase just for balance, but for a plane.
So it's like a short-term fix.
Exactly. Then you've got permanent ballast, which is usually lead blocks or plates.
Mhm.
This is installed more permanently to deal with a balance issue that keeps coming up.
Okay.
It's like adding weights to your car tires. It's there to stay and fix a persistent imbalance.
Interesting. So a pilot might use temporary ballast for a flight that has an unusual weight distribution.
Yeah.
But if the plane itself has a chronic balance problem,
Yeah.
they'd go for a permanent solution.
That's a good way to put it.
This is all starting to click.
Huh.
It's not just about finding that center of gravity.
Hmm.
It's about understanding how weight and balance work together.
Yeah.
And using that knowledge to make good decisions to keep flights safe and efficient.
Yeah.
And, I'm realizing this applies to more than just airplanes.
You're right. These fundamentals of weight and balance are essential for anything that flies,
Okay.
including helicopters.
Helicopters. Okay, now you've got my attention.
Yeah.
Do the same principles apply?
They do.
Okay.
But there are a few key differences. Helicopters usually have a much smaller CG range than airplanes.
Why is that? Because they're smaller and lighter?
It's more about how they're designed and how they fly. Helicopters use that single main rotor for both lift and control,
Right.
which makes balance even more critical.
Uh-huh.
Even a small imbalance can really mess with its stability and how well it maneuvers.
Makes sense.
Right.
So how do they even start weighing and balancing a helicopter? Do they use those same types of scales?
The scales are pretty similar,
No.
but leveling the helicopter is a bit trickier.
How so?
We need to make sure it's perfectly horizontal,
Oh.
both lengthwise and side to side. It's like a perfectly balanced table.
Yeah.
All four legs need to be the same length.
So not just nose to tail level, but side to side level too. That sounds tough.
It can be. They often use plumb bobs to get that perfect level.
Plumb bobs.
Yeah, it's basically a weight hanging from a string.
Right.
When the tip lines up with markings on the floor,
Yeah.
we know the helicopter is perfectly level.
Wow. So much precision goes into every aspect of aviation.
It does.
It really shows you how important understanding weight and balance is.
Yeah.
Not just for the pilots,
Mm-hmm.
but for anyone working on keeping those aircraft safe and in good shape.
Absolutely. And to tie this all together, our handbook dives into a specific example, the Bell Jet Ranger helicopter.
Okay, let's hear it. What are the key things we should know about weighing and balancing the Jet Ranger?
All right, so the Jet Ranger has 3 jack pads,
Okay.
2 at the front, 1 at the back.
Okay.
They lift the helicopter using jacks under each of those pads.
Okay.
And just like we talked about,
Yeah.
they use those plumb bobs to make sure it's perfectly level during the process.
Like a three-legged stool.
Yeah.
All legs got to be the same length for stability.
Great analogy. Once the helicopter's level, they record the weight readings from each jack, just like we do with the airplane.
Mm-hmm.
But we also need to know exactly how far each jack point is from the helicopter's datum.
Right. So we need those distances to calculate the moments.
Exactly. And those moments help us figure out the helicopter's empty weight
Okay.
and the EWCG. It all goes back to those core concepts.
Yeah.
Weight, arm, and moment.
It's incredible how much goes into making sure a helicopter is properly balanced.
It's all about safety and efficiency. And as we look closer at this Jet Ranger example,
Yeah?
you'll see how these weight and balance calculations play a huge role in making sure it flies safe and efficiently.
This is turning into a masterclass in weight and balance. I can't wait to see how it all works out in this real-world example. Okay, so we're back, ready to tackle this Jet Ranger example.
Okay,
We've got our jack points, our plumb bobs all set up.
right.
Now let's see how this all translates into those weight and balance calculations for a helicopter.
All right, let's get into it. Our handbook gives us some important numbers for the Jet Ranger.
Okay.
We know the datum is 100 inches in front of the main rotor shaft.
Right, so that's our starting point, our reference for all the measurements.
Exactly. And the handbook also tells us that the distance from that main rotor shaft to those forward jack points is 224 inches.
So those forward jack points are 224 inches behind the datum.
Oh, you got it.
Okay, I'm starting to visualize the layout here.
Mm-hmm.
We've got our datum,
Yeah.
and then the 3 jack points are at specific distances from that point.
Now, let's say we've carefully leveled the Jet Ranger using those plumb bobs,
Right.
and we've got our weight readings from each jack.
Okay, so we're ready to crunch some numbers and find that empty weight and EWCG.
We are. Let's say the weight readings are like this. 450 pounds on the left forward jack,
Okay,
445 on the right forward jack, and 325 on the aft jack.
perfect. So we've got our weights and distances,
Uh-huh.
time to calculate those moments.
Exactly. Remember, moment equals weight multiplied by arm. So for that left forward jack, the moment would be 450 pounds times 224 inches.
That gives us a moment of 800 inch-pounds for that jack point.
Right. And we do the same for the other two.
Okay.
The right forward jag is 445 pounds times 224 inches, which comes out to 99,680 inch-pounds.
Got it. And the aft jack.
That one would be 325 pounds times 42 inches, giving us 13,650 inch-pounds.
Perfect. So we've got 3 moments, 1 for each jack point. What's next?
We add them all up to find the total moment for the helicopter.
Up.
In this case, it's 214,130 inch-pounds.
Okay, so we have our total moment,
Mm-hmm.
but we need that total weight too to find the EWCG.
You're right. Just add up the weight readings from all 3 jack points.
Okay,
That gives us a total weight of 1,220 pounds.
got it. Total weight. 12,220 pounds, total moment. 214,130 inch-pounds. How do we use these to actually pinpoint the empty weight center of gravity?
We divide the total moment by the total weight. That'll tell us where the helicopter would perfectly balance.
Okay, so 214,130 inch-pounds divided by 12,220 pounds.
Yep.
What did that give us?
An EWCG of 175.5 inches.
So the empty weight center of gravity for this Jet Ranger is 175.5 inches after the datum. That's fascinating.
It is, and it really highlights how important these calculations are. Just by looking at the helicopter.
Yeah.
You'd never guess the balance point is that far back.
Right. I'm really starting to see how all these little things, the weights, the distances, even where they put that datum,
Yeah.
it all comes together to paint a complete picture of how the aircraft balances.
And that understanding is crucial.
Yeah.
Not just for safety, but for getting the most out of the aircraft's performance, too.
Absolutely. I think we've covered a lot today. We started with the basics of weight and balance,
Right.
explored how it works for both airplanes and helicopters,
Yep.
even walked through that real-world Jet Ranger example.
It's been a great deep dive.
It has. So next time you see a plane or a helicopter up in the air,
Mm-hmm.
remember all those calculations, all that planning, all that attention to detail that went into getting it off the ground.
Absolutely. It's a real testament to human ingenuity. And our fascination with flight.
Well said. Thanks for joining us on this weight and balance adventure.
Thanks for having me.
Until next time, keep exploring and keep those wings level.